Thank you everyone for coming today to our workshop on using data to understand climate change. I'm really excited for this. This is part of our series of 4 workshops on climate change in the Southwest. I know many of you were with us on Monday. Welcome to anyone who's new. This is we're going to be going over some of our favorite activities today, so been very excited. My name is Kelly Steinberg, and with me today is Dr. Steph Bestelmeyer and Stephanie Hanamato. We're from the Asombro Institute for Science Education, which is in Las Cruces, New Mexico. We are a nonprofit that serves the students of Southern New Mexico mostly, but all across the Southwest also. We reach about 20,000 students, usually through class visits and field trips, but also through online curriculum like we're doing and sharing with you today. Teacher workshops to share that curriculum. And this year we've added a lot of remote lessons as well. What we do mostly focuses on translating scientific research for the classroom. And so this idea of using data really fits into that because we love to take data that scientists are collecting, scientists have put out into the world, whether it's online or through their papers, and figure out how to translate that for our students and your students. Today we are partnered with the USDA Southwest Climate Hub. About 6 years ago, the Climate Hub partnered with us to create education materials to publish online. These materials are about preparing future decision makers, our students, to be informed decision makers about climate change. We currently have 3 modules: climate change in the water cycle, the effects of climate change on agricultural systems, and climate change and the carbon cycle, published online. In those are 17 lessons. They could all be taught as these modules, but they can also be done individually. I know there's 4 informal educators on the call, and so thinking about how do we take pieces that work for us and mix and match them into everything we're teaching. These are made for informal as well as formal educators. And in each lesson, there's educator guides, slides, materials, videos, student handouts, whatever you think you'd need to teach these lessons. Today, we're going to give you an overview of a few of those, but we'll start with a talk from Dr. David Gutzler at the University of, or supposedly retired from the University of New Mexico, as he introduced himself in the chat, to talk about data. And then we'll show you how to access all of these resources. And then we'll spend the majority of today actually doing some of the activities and give you some experience. Think about how you could bring this into what you do with your students, play some games, work together in small groups. And then in the last few minutes, we'll do a little wrap up. We've got some prizes, some classroom materials to raffle off that we'd love to send to you. So that's our plan for today. We're going to jump in with our guest speaker, Dr. David Gutzler. He is trying to retire from the University of New Mexico, but he keeps agreeing to do things like this. And he was with the Department of Earth and Planetary Sciences. When I was at UNM a few years ago working on my master's, I took a climate dynamics class with Dr. Gutzler, and it was one of the most interesting and kind of practical classes. I learned so much about how to interpret what I see in the sky into what's going on in the climate. His research is on climate and atmospheric sciences, and he's going to give us a little bit of an introduction today into how data is so important to understanding climate change. I know that's a huge topic, Dr. Gutzler, so take it away, give us the quick version. And I will stop sharing and you can screen share. Oh, and I should say Dr. Gutzler has also recently retired from our advisory committee with the USDA Southwest Climate Hub.
Okay. There, do we have sound on a slide?
Yes, sir.
Okay. Um, yes, I guess I did successfully retire from the advisory board, sort of. I mean, I still keep in touch with folks. Um, Kelly asked me to talk about how climate data feeds into climate models in 15 minutes, which is an astoundingly wonky subject. So let me apologize in advance. So I think I've got 4 slides or maybe 5, and 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 we'll just go what you are looking at or will be looking at, according to what Kelly told me, is some climate model output. And so what I will try to do here in just a few minutes is show you some pictures to get over this problem that we face sometimes, that I've run into talking to legislators and skeptics and folks like that, who just say, it's only a model. So let's talk about how we use actual observations and how that goes into what we call a climate model. And so there are 3 kind of ways that occurred to me that data and model are intertwined. One is called validation. The other is downscaling, and we'll take a look at examples of those. And then there's a third aspect of this, where the data and the models get totally intertwined, which is a really wonky subject called data assimilation. And I won't cover that, but you can ask me about it if you want, or you can just make me go away, which might be a better choice here in 15 minutes. So that's what we're going to do. So we're going to use data, and we're going to feed those into what we call dynamical models. And we use the dynamical models to make projections of climate, and you will be looking at the output from those models. Okay, so this is going to be on the exam, so everybody pay attention. This is a slide that we could ask Kelly to describe it, because I cribbed it from my grad class that she took. So this is what a model is. So and all we need to know, you don't need to, we won't go through all the terms. All you need to know is that that's real physics there on the left. Those are equations that are simply, he says, we love to humiliate students with qualifiers like that. And I'll note that these are called the primitive equations. But the basic idea is that we can use really basic physics, conserving mass, momentum, and energy. And that's what these equations are doing. And by conserving mass, momentum, and energy as air in the atmosphere and water in the ocean moves all around, we can create a dynamical model that accurately simulates in a realistic way how the atmosphere behaves, just using physics 101 stuff. And so the idea is that we're going to carve up the atmosphere, in this case, into boxes, and like the boxes shown on the right. And we're going to apply physical equations that nobody, even the most ardent climate change denier, could deny if they know any physics at all, and develop a dynamical model that evolves in time. So all those terms on the left-hand side of those equations are time dependencies. So if I know the temperature and the pressure and the water content and the winds in each one of those boxes at some time, I can use these equations to project how the atmosphere evolves to the next point in time. And that's what those equations do. Okay, that's just basic physics, but there's we need to use data in 2 ways. One is that some of those terms we can't really deduce properly without just sort of tuning the model to simulate reality. Like those capital F's in the upper right-hand corner, that's friction, that's changing the winds. And the only way to simulate friction on the scale of these boxes is by kind of putting in a number that gives us the right answer. And we use data for that. All right, so the models are tuned a little bit. And that's number one. But then having done that, we only use one number for friction all around the world. And then once we've got this model running and we push the button and it's simulating the evolution of winds and temperature and pressure and so forth, then we need to know, is the model generating the right answers? So we go through a process called validation. And I'll show you an example of that here. So this curve is from the last National Climate Assessment, and that yellow curve that's jaggedy is actual data. So this is averaged over the state of New Mexico, and it shows actual spatially averaged data from actual thermometers across the state of New Mexico since 1900. And what we want our models to do is to simulate roughly how that curve looks. We don't expect our models to get every jaggedy up and down because the models are simulating kind of natural variability, just like we wouldn't expect a weather forecast model to simulate weather a year from now. We just want it to simulate accurately for a few days and then get the statistics right after that. So we want to know if our models are getting the statistics of that jaggedy yellow curve correctly. And that's called validation. And that's what the gray shading indicates. So if we run a whole bunch of models, starting from different specific days and averaging over different models, then the envelope of variability described by those models is that gray shading. And the claim is it looks pretty good. Right? So if we think that gray shading indicates that the models seem to be doing kind of the right thing, simulating New Mexico temperature, then it increases our confidence that if we change CO2 levels going out into the future, out to year 2100, like the red and green shading, that maybe the models are giving us a reasonable projection, given that they've produced reasonable results for past climate variability where we know what the right answer is in terms of temperature, right? So that's called validation. And that's one way we use models to try to get, to use data to help make our models better. Then there's another problem. And let me go back here. The other problem is that those boxes are too big. If you look at those boxes like in the upper right, one box that's one temperature and one pressure and one value of wind is roughly the size of the state of New Mexico. And we can't really make our models too much smaller. They get smaller with time, but the way the dynamics works in those models based on the equations still gives us averages over really big boxes, like this black square here. That's one climate model grid box. And so this is from a paper that I wrote with a student in the class that Kelly took about a decade ago named Tom Kennedy, who's still rattling around UNM. And he was interested in how climate change might affect Gila trout. Well, Gila trout only live in the headwaters of the Gila River, which is one tiny little corner of this big box. So we needed to downscale the climate model output. And there's a number of different ways to do that, but a real common way is to take observed data and then take climate model output over this big black rectangle and use data to kind of statistically generate high resolution variability that's artificial, but is realistic at much smaller scale where it can actually be used by people that are interested in what's going to happen where they live, not over this gigantic rectangle that includes the whole Central Valley of New Mexico, plus the San Juan Mountains, plus the Navajo Reservation, and everything in between. And so the data that you will be looking at coming out of climate models has been statistically downscaled like this to a resolution of 4 kilometers. And it's important to keep in mind that that downscaling is statistical. It's not based on real physics, but it's designed using a kind of a complicated statistical formula to be realistic. Okay, so there is an example from the website that you're looking at, and it's showing climate model output at county scale. So let's just in 1 minute review what we've just talked about, that we're using global model output generated over really big boxes, and this MACA data archive that's on the Climate Hub website uses 20 of those models. And this particular plot is averaged over all 20 models, each of which was validated with actual observations. Then for the historical period simulated by those models, they've downscaled the climate model output to 4-kilometer resolution and bias corrected it. And then what we're looking at here are future simulations of what's likely to happen based on a particular guess as to what greenhouse gas concentrations might be. This is a high resolution output, I think. And they've statistically downscaled the output to high resolution, 4 kilometers boxes. And then for this particular plot, then they've taken all those little 4-kilometer boxes and averaged them to counties. And so that's the data that you'll be looking at. Okay, so if that's enough wonkiness, that's how we go back and forth between data and observations to get the numbers that I think you're going to be cranking out and playing with at county scale. So it's based on big global models run at very coarse resolution, statistically downscaled to a resolution where we can then upscale it back to sort of a useful county level output. Okay? I'm happy to address any questions unless you just want me to go away, but thanks for the opportunity to regale you with the nuts and bolts of how we mess around with climate model output to try to make it useful.
Thank you so much, Dr. Gutzler. That was so much information, and you got it all in there. Very nice. We do have time for 1 or 2 questions. If anyone has one, you can either shout it out or put it in the chat. All right, looks like I see some super interesting, some great comments. You have another slide you want to talk about?
That's the wonky stuff. I think we've done enough.
All right. Well, thanks. I know that was a lot.
It was a lot.
Everyone's heads are spinning a little bit, but I feel like that's a lot of context that I don't know if I remembered or knew. Oh, we do have one question of how accurate are today's weather forecasts?
Okay. Well, they're really accurate. And you know, I'm old. And so let me tell you, I grew up in San Diego on the coast. And the joke there when I was growing up was that the weather forecast was essentially perfect, except for about 10 days a year. And those 10 days a year happened to be the days when it rained, and which were the only forecasts that anybody cared about. But other than that, you could look out the window and say tomorrow is going to be just like today. But we do a lot better than that now because these models are so good. And the Weather Service has statistics to prove it. So weather forecast, the kind of model we just looked at really was a weather model. And the climate models that you'll be analyzing really are just souped up weather forecast models. The big difference is they're coupled to another dynamical model of the ocean, and the two interact together. But for a weather forecast, you don't need to worry about the ocean. The ocean is not going to look too much different a week from now than it does today. So we can get away with treating the ocean as just being a surface of water that doesn't change. For a climate outlook for 50 years from now, you can't get away with that. But for a weather forecast model, these dynamical models are so much better than they were, in part because the model is better, and in part because the initial data that we use to start the model is so much better. That was the real problem in San Diego when I was a kid. The models didn't know what was coming off the oceans because we didn't, we looked to the west and you couldn't see over the horizon. Satellite data wasn't really very good. And so the models just missed it. But now they get it. And in part, and I'll just leave it at this, in part, the reason that the weather forecast models are so good getting started with today's weather to use as a start for that model is because of this data assimilation process, which is an improved way of taking observations and interpolating the observations onto really fine grid cells using the model itself. So what we call an observed weather map, which is what we're looking at here from this morning, really is model output, but it's this morning's weather observations run through a model to come up with a nicely interpolated map of this morning's weather that is completely consistent with those physical equations that go in the model, which turns out to be a really important thing to do to make your model forecasts accurate.
All right.
Thanks for the question.
Thank you so much, Dr. Gutzler, for joining us. You're welcome to stick around. We're going to dive into those maps in a little bit. But I think if anyone else has a question they want to chat with Dr. Gutzler, if you have a few moments, you can look at the chat, but we'll move on.
Sure. Okay, and I'll be around for a few minutes, but then I'll have to take off myself. So
great. All right.
Thanks again.
Okay, I'm gonna take back the screen. All right. Excellent. So as I mentioned earlier, we've got a lot of materials online that you can access. And the activities we'll be doing today that you can do with students, that you can take into classrooms, come from this online materials. So everything is at asombro.org/climate is the easiest way to access it. And we currently have 17 lessons organized in 3 units. Lesson 18 will be up just as soon as our web person can get it up. And they're put into 3 units, but they can be done individually. We were hoping that they could build off each other, or you could feel free to take one and do it as a standalone. And as I said, we have educator guides, student handouts, presentations, printable materials, as well as instructional videos. So many of the lessons we'll be going over have a video that you can watch to show you how the game works, or how to put the materials together, how to prep a demo or experiment. Today we're going to cover lessons from 2 of our units, the water cycle and carbon cycle unit, but there's also the agriculture unit that we've covered last time, and we'll cover more next time. Where am I? So asombro.org/climate is the place to access all these. This is our web page. Here you see access to each of the units. Water cycle is in both English and Spanish. And there are also videos linked here. Access to all the videos that we have are on this page. You can scroll through and find each of the different units. And I'll click and take us to the water unit. This takes us onto our Southwest Climate Hub website. And it's all arranged as if you were doing a 10-day module here. But you can find, as you scroll down, find each of the lessons. So day 1 is an activity called Insulating You, Insulating Earth, which we'll go over next Wednesday. It's a really fun experiment. And you can see the educator guide, the student handouts, the PowerPoints, and a video. Everything you need is right there. And all the units are set up like this, where you can click through everything. So that, again, easiest way to find it all is asombro.org/climate, and I will email you links after this workshop with links to this page, links to this page, and links directly to the activities that we'll be covering. So I'm going to go ahead and jump right into our first activity that we'll be doing today. If you were with us on Monday, Steph previewed this a little bit. It's our climate data jam, and we'll spend a good chunk of time on this today. A data jam is a model Sombra developed and has been using for 10 years, is now in use all over the country. There's a few main components of a data jam. Students look at real world data, identify data trends, and communicate that trend creatively. So the core of the data jam is this communicating climate data to non-scientists in a way that anyone could understand. So some examples of what that creative communication looks like is here on the screen. This picture here, these two pictures come from a data jam project where students were using data on kangaroo rat populations from here in Las Cruces. They had data on the population size over several years. And to show that, they made a bunch of these kangaroo rat piñatas, and the circumference of the piñata was scaled to the number of kangaroo rats in the population that year. So you can see as you look at all of them, some years we had very few, some years we had a lot, but most years it stayed pretty consistent. This group down here, it was Halloween, so they're all dressed up, but they used music. They actually composed music to represent climate data, and they used low notes to represent low temperatures and high notes to represent high temperatures, and played their musical composition together for their class. So we'll be using precipitation and temperature data for the climate data jam, and you'll be looking at some interactive maps. We suggest this lesson as a total of 4 hours over 4 days. However, we've done data jams in an hour. We've done data jams, we've had teachers who do it over a month. So the educator guide is set up for that 4 hours. It's definitely flexible. But one of those days is a sharing day and having students present and share and kind of compare the trends they all found, look for patterns in their overall data analysis. So we're going to be looking at precipitation data and temperature data today. And we're going to send you to a website. This is the model Dr. Gutzler was talking about, where this interactive map has county level data. So you can click on any county in the country, and it will give you, this doesn't match up with the county here, but it'll give you the current or historical data for all the seasons and annual, future predicted by the models, those 20 models combined, and that was 2040 through 2070, I believe. So if you think about our students who maybe in middle school now, this is when they're in their 30s, 40s, 50s, this is their lifetime. What will the precipitation be? And then the changes here as well. So we're going to send you to these websites, have you choose counties, look through, click on a county, and record this data. This precipitation, I'll also point out, is in millimeters. You can do the exact same thing with temperature. There's a maximum temperature map. There's also a minimum temperature map that you can find on the website if you would like to look at it. But we'll have you look for data trends in the temperature as well, and this is in degrees Celsius, you'll note. And what you're going to do is go pick a county, look through that data, and identify a data trend. So a data trend is a pattern or relationship between two variables. Some examples. In San Diego County, California, the predicted decrease in mean annual total precipitation is relatively small. However, in the spring, the predicted decrease is large. So when you look at this data table, you see spring is 14 millimeters decreased, but annual average is just small. So there's not a large change, but overall, but definitely a large change in this season. So your data trend could just be kind of comparing two numbers. That's totally fine. A data trend might be a pattern across the whole year or across space, maybe. We tell students to look at one county here, and I suggest that since we have limited time today, you'd stick at one county, but students could definitely compare across areas too. So another example, in Doña Ana County here in southern New Mexico, temperatures are expected to increase by at least 3 degrees Celsius in every season. And you see that when you look at the data table. So that's a data trend. Both of these sentences, one sentence to describe something happening in the data. That's our data trend. And then we're going to show that creatively with the project, whether it's writing a musical composition, making piñatas, writing a poem or a song or an infographic of some sort. So what I'm going to do now is send you into breakout rooms and have you give you the chance to look at the maps in small groups. So when we send you into breakout rooms, you'll see your room number will show up. You know, it'll say join breakout room number 4 or something. And we'll also put a link in the chat right now for this Google folder. So in here, you'll find your room folder and open it up. And in there, you'll find a climate data jam spreadsheet. And so in this spreadsheet, you're gonna choose either, you have the links here for precipitation data and temperature data. You'll choose one and choose a place to look at as a group. If you want to put the data in here in this worksheet, you can. We have students fill the data onto a worksheet in the lesson. And as a group, find a data trend. Choose a data trend that you can represent with a creative project later. We'll give you about, I think, 8 minutes. Oh no, you're being asked. Okay. I will try and solve the access. Is it you can't open the folder at all? Or is it the little folders?
Can't open the folder at all.
I think I can fix that easily.
Denied.
Okay. Try now. All right. So we'll give you about, there we go. I think 7 or 8 minutes. I'm depending on how far behind we are, Stephanie, in the breakout rooms to find a data trend. We'll come back. I'll tell you a little bit about the creative project and how we talk through that process, and then give you more time to make a creative project. So I know that's fast. And we just are giving you a taste. Again, you'd give students a whole class period to do this. So what you just did in 8 to 8 minutes, students would have lots of time to look and think and figure out what they're doing. So hopefully you all found a data trend or came up with some ideas of data trends as you were in your breakout rooms. Because now we're going to take those trends you found and translate them into some sort of creative project. So I have a couple examples of ways I might do that. For example, if you're a visual person, artistic in drawing or painting or clip art, you might do an infographic. So this is our data trend again in San Diego County, California. The predicted decrease in mean annual total precipitation is small, but large in the spring. So I made a clip art infographic where I have all the seasons represented. I have, I probably should have labeled them if I was really, really on my infographic game, which I didn't think about till now. But I've got a title, I've got a key that explains a blue range. Blue means an increase in precipitation, red means a decrease in precipitation, and my scale that 1 raindrop equals 1 millimeter of change in precipitation. I did round, and that's all right. So there were decimal points and I didn't use them. But in each season, I have the number or the raindrops to represent the change in precipitation. And then in the middle, I have the total annual change. So you can see that the one big change, or the outlier is the difference here in red, whereas all of these are much smaller changes and what that means for the annual. So an infographic is something, you could look at quickly and show more than just a pretty graph, but something using symbols or pictures usually. However, if you're a person who likes words, writing, music, poetry, you might want to write something. So this is our data trend from New Mexico, Doña Ana County. Temperatures are expected to increase by at least 3 degrees in every season. So I wrote a series of haikus, one for annual and one for each season, to explain the data. I didn't need a scale or a key for this one, but I used the data itself in every haiku. So temps rise in NM, 3 degrees hotter all year in Doña Ana. We don't get much snow, 3.1 degrees higher. Will we get snow days? I'll let you read the rest if you like. But the data itself, the numbers are in the data trend or in the creative project. So it's still communicating data, just not in your typical graph or data table. So we're going to challenge you to take that data trend that you found and make a creative project. You could, you're working with your group, so up to you. I'm sure you've got some virtual group work skills from the past year. You could use Google Docs. You could you could write something up together. You could use clip art. Someone can make a drawing. You could all go take a picture. I don't know. But poems, rewrite the song lyrics to Twinkle Twinkle Little Star, anything you can think of that you can put together in the next, say, 8 or 9 minutes. And then we're gonna have time to share out a few of them. So does anybody have questions before we send you back into breakout rooms? Does that make sense? All right. We'll send you out and we'll call you back to see what you are able to do in that time. And again, this is something you give students maybe 2 days to do. So it's a challenge to do it in this short a time. Well, again, I know that was short. I know probably not enough time for all your creative juices to come to fruition. But hopefully you had fun and you came up with something quick or got started on something. Would anyone like to share their creative representation of their data trend? If you would, you can unmute yourself. We have time for maybe 2 sharings. You can unmute and you can share your screen if you'd like, or tell us in the chat what you did.
We're from number 3. Can I share my screen?
Yep. Here, I'm stop sharing. You can
I'm
share.
going to try. Wait, went away. So we were looking at a couple of, we wanted to do a comparison within New Mexico, where most of the people are from. And so the top one, you can't see terribly well, but this is the top one is the change in rainfall that's coming per season. And then below is the change in temperature to get an idea of how they are, how they might be connected. Yes, I should have done a regression. No, I don't remember how to do it with 2 values on that and getting the scales right. So here's what we did. And, I mean, obviously there are substantial seasonal changes that would be happening. For those of you who don't know, I didn't know, Eddy is in the lower part of the state. It's where it's in the seems to be mainly Sonoran Desert. It is where the Carlsbad Caverns are, and Rio Arriba is in the northern part of the state by the Colorado border.
Excellent, thanks. All right, so yeah, you guys were able to show the data, gather the data together, show it here. And so I know we do tell the students a pretty graph is a creative representation, but we tell them they got to do more. But we'll give you a break since it was short time. Anyone else want to share? Thanks so much, Joe.
Sure. How do I unshare?
Up at the top, there should be a red button, stop sharing. And Beverly, is your hand up?
Yes.
All right, would you like to share?
Yes, as soon as he stops.
Okay.
I'm having trouble getting there.
Okay, Beverly, if you hit screen share, it might give you.
It won't do it.
Okay.
I'm stuck on the Excel. That's so weird.
Okay, I can take over, and then
it may also say view options at the top of your screen versus a red.
Oh, okay. There we go.
There we go.
In Bernalillo County, there is less rain in the spring, which means we have dead and dry vegetation, which causes fire risks.
All right.
That's all we got in that amount of time.
That's fair. All right. Yeah. Short amount of time. Very nice. All right. Yeah, absolutely. So, and then we ask the students to make sure the data itself, the numbers of the data are represented in here too. So that could be with the size of the pictures. It could be with the the words you use. There's all sorts of ways you could do it. But yeah, very, very nice start towards your creative representation.
Can it also be in the increase in fire risks over the years?
Yeah, if you showed somehow the increase in fire risk over the years. The one thing I would caution there is the data that you have is about precipitation, which leads to fire risk, increased fire risk.
Right.
But the data itself is about the rainfall.
Right.
And so we often, especially with students, because they'll kind of get ahead of themselves with that. And we want to really focus on what is this data telling us? Not what do we know about rainfall and fire, but what is this data telling us?
Mm-hmm.
So very nice. Excellent. Well, thank you all for sharing. We are going to move on from the data jam. Hopefully you can find a way to use a data jam. It's one of our favorite lessons, our favorite things to do, and you'll really be surprised by what your students can come up with and what they can show. And there's a lot of resources we have online, including a mini data jam YouTube video that walks students through how to do that on their own. We made it for during the pandemic when we knew they would be at home. I'm going to pass it over to Stephanie.
All right, thanks, Kelly. So I wanted to introduce you to an activity called Up in the Air, and this is part of the carbon cycle unit. It addresses the phenomenon, how are humans impacting the cycling of carbon on Earth? This is a two-part lesson, so you could conduct it during 2 class periods, or you can combine it if you have a block. However you'd like to break up that 90-minute chunk. There are instructional videos for both parts of this lesson. They're excellent videos. Just keep in mind, as you listen to this, we're going to go through this really quickly today, but the instructional videos are available to you at any time that you want to watch them. They're on demand. So you can come back to these videos at any time, so you don't have to remember all of this. Please keep that in mind. Speaking of that, the links for this lesson and the instructional videos are going to be in a PDF that we're going to send to you by email afterwards. We'll also put it in the chat during this presentation. All right, so I wanted to just give you an overview of both parts of these lessons. So part 1 is a qualitative model. It involves a beanbag toss. So you can see in that photo down on the right, students actually cut yarn to scale a model. So what they're doing is trying to model, they are modeling the carbon reservoirs of the Earth with these scaled yarn models. And these are the reservoirs that the students will be aiming for as they conduct a beanbag toss. Now, the models are scaled to the petagrams of carbon that are contained in each of these models. The ocean is the largest reservoir of carbon on Earth. It has over 40,000 petagrams of carbon. Now, a petagram of carbon is a really, really big number. It's equal to a quadrillion grams. To make that a little easier to understand, we tell students that it's equal to the weight of about 6 million blue whales. So that kind of gives you an idea of how big of a number that is. They toss the beanbags to each other. They say the carbon cycle processes as they toss the beanbags, aiming for those scaled reservoirs. They also conduct a sorting it out activity. So this introduces them to the carbon cycle processes. They look at the compounds involved in the processes and sort them out on a page. And as they do that, they also name the processes involved in the carbon cycle and fill out the bottom of their handout. Page 1 has this carbon cycle diagram. Then they've got this handy diagram that has all the processes labeled that they can then use throughout the rest of this lesson. And you'll see why this is going to come in handy in just a moment. All right, so that's the first part of this lesson, kind of in a nutshell. Again, I went really, really quickly. It's a really fun activity, and it's all contained in the instructional guide, and there's a video as well. The second part of the lesson is a quantitative model of the carbon cycle, and that is done through a board game. So students move carbon through 1 year of the global carbon cycle. In this game and in the real global carbon cycle, there's carbon that moves and carbon that doesn't move. Most carbon actually stays put in the course of 1 year. That is called non-fluxing carbon. So that's carbon that does not move. There is a little bit of carbon that moves over the course of the year. That's called fluxing carbon. So fluxing carbon is carbon that moves between reservoirs in a year. So students conduct this game with a game board that has all of the reservoirs listed. It looks a lot like the diagram that I showed you on the last slide, with some pieces that are cut out, and those pieces represent fluxing carbon. And then with some game cards. The game cards have the name of the processes and how much carbon is moved from one reservoir to another, again in petagrams of carbon listed on the game cards. So we're going to have you acting as students to give this game a try. Now, you don't have any game cards or a game board in front of you. So what we have for you is a modified version, a virtual modified version of this game that you're going to be conducting as a Google Slides. And you'll find it, again, we're going to put you in a breakout room, and you'll find in that same folder, so you're going to want to pay attention to the number of your breakout room, that you'll find this, you'll see these instructions and this game board. So you're going to have about 6 minutes to play around with this in the breakout room, but in your class, you can expect this to take about 10 to 15 minutes for students to complete. So we think you're advanced and you can do this more quickly, and we want to just give you a chance to mess around with it. So there are instructions, like I said, on slide 1. You'll take turns with your partner to move the top card on the right of the Google slide into the boxes on the left side of the Google slide. You'll have one person be player 1 and one person be player 2. You're going to determine where the carbon is moving to and from using the carbon cycle diagram, like the one I showed you a moment ago. That is actually available to you when you get to your Google slide deck. You'll see it as slide 3. You're going to subtract the amount shown on your card from the reservoir that carbon's moving from and add it to the reservoir carbon's moving to. And that'll become more clear as you get in there. So if you're not sure what I mean, you'll see what I mean when you get in there. If you need a calculator, you can either use the one on your phone, or we have a link to a calculator on slide 1. So after you play the game, if you have time left, you'll go to slide 4 and answer a few questions. Did anyone get to answer that last question? How many blue whales worth of carbon ends up in the atmosphere every year? No.
I accidentally did it as both players together rather than both players separately. And so then when we got to that last page, we're like, oh, we did it wrong. And then boom, we're back here.
All right, well, the answer is 36 million blue whales. So students see that a lot of carbon ends up in the atmosphere. They see the flux from fossil fuel reserves results in an increase in atmospheric carbon. And they see that humans are impacting the carbon cycle and affecting Earth's systems. So with that, I will go ahead and pass it over to Steph, who's going to tell you about another fun activity.
All right, thank you. And Kelly, are you going to share or do you want me to share? Oh, great. Thanks, Kelly. So I get to wrap up, and this is a really simple activity. You are not going to go to breakout rooms. I just want to tell you a little bit about this one. It's called Rainout Shelters. It is part of Climate Change in the Water Cycle Unit. And it's a very simple activity that gives students real data from an ongoing study where scientists are using data to try to understand the effects of climate change on, especially on plants in the desert. So it's based on a study being conducted by Dr. Osvaldo Sala at Arizona State University and his team. Next slide, please. Thanks, Kelly. The experimental setup is really quite clever. They have set up what are called automated rainfall manipulation systems. We call them rainout shelters for obvious reasons. And these are just areas that cover plots. So you can see here on the left there, that blue covered plot is called the interception plot. And there's acrylic slats over part of that rainout shelter that can intercept either 80% or 50% of the rain that would normally fall on that plot. And then the rain goes from that slat into a gutter system, and it's collected in a tank. And then the water from that tank is pumped into other plots. So what we end up with is 5 different plot types, going from least amount of water, which are the ones that have 80% rainout shelters over them. There's also plots that intercept 50% of the rain. There's control plots, and then there's 50% and 80% irrigation. So those 80% irrigation plots receive 80% more rain than the control plots do. All right, and next slide. So the setup and the materials for this is very simple. You will have a teacher's guide you can access, and there's a 4-page handout to give to students, and there's an answer key for you, and that's the whole that's this whole activity. So on page 1 of the worksheet, which you can see over there on the left, it tells a little bit of the background about this ongoing study, and then very importantly, it shows you what our predicted results would look like under 2 different scenarios. So the one in the middle is a graph that shows what would happen, or what we think the data would look like if water is the main limiting resource in the desert. So on the x-axis, it goes increasing water. So on the left side, those are the plots that are 80% rain out. And then as you move to the right, you're getting plots with more and more water. So under this scenario, we would say if water is really the only thing limiting these plants from being able to grow, then we would expect as you increase the amount of water you give these plants, then the plant biomass, or the amount that the plants are growing, which is shown on the y-axis, would just continually increase. So that's one prediction. The alternative prediction is that if water is just one of the limiting resources, and maybe something else is limiting, something like nitrogen, for example, then we would expect, as we increase the amount of water at some point, and we don't know where, we would expect there to be a plateau where you can just keep adding water, but there's not an appreciable increase in the plant biomass. So all of that is explained pretty well in the first page of the handout. And then as the students move forward on the next slide, there are the actual data. And this is just a subset of the data. We've taken the results from 5 plots in 1 year for each of the 5 treatments. So on the top, you've got the rain out 80% plots, and on the bottom, you've got the irrigated 80% plots. So students through this worksheet will walk through the data analysis, which in this case is just calculating the mean biomass in grams per meter squared per year under each of these plots. And the next slide shows the next page. So now we're all the way over on the right side of this. And this is the 3rd page of the handout, which asks students to think about what the variables are within this, the independent and dependent variable. Then they graph the data that they just took a look at on the previous page. And then it steps them through thinking about what the results mean and a little bit of interpretation on the final page of the worksheet. So teachers have assigned this as homework. Teachers have allowed their students to work on it in one class period. There's been a lot of different ways that teachers have given access to this, but it's a great, very simple activity if you want your students to really understand an ongoing research study that's being done, in really kind of a neat experimental setup to learn a little bit about how we can use data to understand the effects of climate change on plants here in the Chihuahuan Desert. And I'll pass it back to you, Kelly.
Thanks, Steph. Yeah, I really like that one after the data jam, where we thought about what's precipitation going to look like in the future, following that up with, well, how does that affect our plants, and what do we see happening right now? I think that's a great connection there. So that is all we're going to do today. We've covered 3 lessons from 2 of these 3 units. So there's lots more that we have available online, and we will be covering most of them in the next 2 workshops we'll be doing next week, Monday and Wednesday, 4 o'clock Mountain Time. We'll be back here again to talk through more of these lessons, and again, give you time to play around with them and get just a taste. There's also new stuff we're always coming out with. Our newest lesson is water conservation in the Southwest. Where's our water? Which uses data from across the Southwest. Students are looking at water into the future. How are we using water and population growth? And at that one, we designed this year for remote learning. So it could be done in class together, or all online with students watching videos and analyzing data that way. But then we also are working on a climate change and wildfire unit. We're just waiting to get back into schools and pilot test those lessons with students. And then another data jam, the water conservation data jam, which is a big data jam project. That one you could drag out for weeks if you want, and a lot of fun too. So those will be coming hopefully by the end of the year up on the asombro.org/climate website. That is all we're doing. We do have some raffle prizes to give away. We have some class sets of the Up in the Air board games. So that board game you just played on Google Slide, we have the game boards and all the pieces that students would actually be moving, kind of like making change between the carbon reservoirs. And so Stephanie did a drawing of everyone who's here. And Stephanie, do you want to tell us who our winners are?
You bet. We have 5 random raffle winners. They are Miss Green, Miss Pape, Yvonne. I'm sorry, Yvonne, I don't want to butcher your last name. Yvonne A, Karen Hagel, and Adrian Hunter. So I'll put those names in the chat. And if you could please send me a personal message with verifying your address, so we can make sure to get those to the proper addresses for you.
Yeah, let us know. We'll send those your way. And we hope you make good use of them. We are always happy to help people find the resources they need. So if you need help with, if you need help getting all this printed out and stuff, let us know and we'll do our best. Lastly, but not least, if you would not mind filling out an evaluation form, if you were here on Monday, it'll look very similar, but it really helps us to just have some anonymous feedback. And just so you know, we have upcoming workshops again next Monday and Wednesday, as well as a workshop at the New Mexico STEM Symposium if you're a public school teacher in New Mexico, and some about ranching and cattle coming up in the fall. And then all I have to say is please stay in touch. We have made contact with many new people through these workshops, and we are if we were in person, you'd be our new best friends, and we'd love to have conversations and get to know you. As it is, it's a little harder, but let us know how things are going. If you have any questions or any problems or notice a typo, let us know, and we want to hear about it.